Hello everyone, I'm Dr. Vilay Khan. Welcome to the lecture Digital Logic Design. Today in this lecture I will talk about encoders and multiplexers. So let's start with encoders. What are encoders? Encoders are combination circuits that encode discrete information using a binary code. So, for example, this is an 8 to 3-bit encoder. When this gets discrete information, 8-bit discrete information, then this encoder encodes the input 8-bit discrete information into 3-bit code. Uh, uh, Encoders are used in computers and digital systems where discrete information is encoded for storage or for transmission. We will see a number of examples in coming slides. So this is an 8 to 3-bit encoder that takes 8-bit discrete information and then encodes them into 3-bit using binary code. Here we have an example octal to binary encoder. This combination circuit takes 8-bit input and gives 3-bit output. So at the input we have 8 digit octal digit 0, 1, 2, 3, 4, 5, 6, 7, and it gives 3-bit output. X, Y, and Z are the three outputs. So it encodes 1 digit pressed or given as input at a time into 3-bit binary code, and this is the binary code, 3-bit binary code represented with three Boolean equations x, y, and z. So this is the Boolean equation of the first bit. X is equal to d4, d5, d6, d7. These are the input variables, Boolean variables. The second bit y is equal to d2, d3, d6, and d7, and similarly z is equal to d1, d3, d5, and d7. Each of the input variable represent an octal digit. For example, this is digit 0, digit 1, digit 2, digit 3, and until up to digit 7. So this is an 8-bit octal to binary encoder, which takes an 8-bit input and gives 3-bit output. Let me show you how can we derive these Boolean equations of this octal to binary encoder. This is the truth table of octal to binary encoder. These are the inputs column, these are the outputs column. And the input is the octal to binary encoder takes 8-bit input. Here we have 8 Boolean variables. They are D0, D1 till D7, and these are the outputs, X represented with X, Y, and Z Boolean variables. So to understand, whenever a user press or give an input, only D0 is 1, which represents that the digit 0 has been pressed. For example, our 0, the digit 0 has been given as an input. For example, there can be a button connected with this octal to binary encoder where the button would represent 1. Whenever the user press 0, it would give 1 input on the first input line D0, and it would the rest of inputs would be zeros. So only D0 would be 1, all the rest of inputs would be zeros, and the output should be as digit 0, and the binary is 0, 0, 0. So the output should be 0, 0, 0. All the three output lines or variables should be 0. Similarly, if there is if the user presses another button, for example, presses button 1, then the output should be the binary equivalent of digit 1, which is 001, and that is represented like this. Okay, so only the second row shows that only this D1 would be 1, and all the other input values would be variable should be 0, the value of all other input variables should be 0, and the binary equivalent of digit 1 is 001, as we know from the octal codes. And similarly for the digit 2, only the input variable d2 should be 1 and all other should be 0, and the binary octal the binary code of the octal digit 2 is 010. Similarly for digit 3, it's 011, and we can continue this way for all other digits. One important thing to note about the inputs is that each time only one input digit is 1 and all others are 0 at that time, and the equivalent binary codes are given in this column. To derive the equation, we have three output variables x, y, and z. So let's consider the Boolean equation of x, Boolean variable x. So just write the variables in the input where this x variable gives 1. So the last four rows of x gives 1. So just consider the corresponding input variable. So x is 1 when d4 is 1, or x is 1 when d5 is 1, or x is 1 when d6 is 1, or x is 1 when d7 is 1. So we can write this logically: x is equal to d4 or d5 or d6 or d7. So this is the Boolean equation of x. We do not need to create maps because it is very simple to write it, or otherwise we would have to write 8 variable map, which is quite complicated, as only one variable input variable is 1 at one time. So it is very simple, just or the input variables where the output is 1 at that particular time. For example, for the x, the last 4 values are 1, so we just ORed the input variables where they are 1. So d4 is 1, d5 is 1, d6 is 1, and d7 is 1. Similarly for the other variable y, these two values are 1 in these two rows, so and the corresponding rows in the input columns, only d2 and d3 are 1. So d2 and d3 are odd, plus the last two rows, so d6 and d7 are 1 in those rows, so d6 and d7. So y is equal to d2, d3, d6, and d7. So this is the Boolean equation of y. And similarly for the z, every other output is 1. So every other input variable is odd. So d1, because in this row z is 1, and then d3 is odd, d3 because in this row z is 1, plus d5 because in this row z is 1, plus d7 because in this row z is 1. So wherever the output is 1, just or combine the corresponding d where the input value is 1 and plus them, make just put the plus sign between them, and that is the Boolean equation of that output variable. So we just have derived the output Boolean equation for the output variable z, which is this one. So exactly these equations have been sketched in the diagram which I just showed before. Here is the diagram, the logic diagram of the octal binary equation. These are the Boolean equation we have just derived. Okay, so multiplexer. The next topic is multiplexers. What are multiplexers? Multiplexers takes multiple inputs. These are combination circuits which takes multiple inputs and steer them to a single output. For example, here in this example, it's an 8-to-1 multiplexer. It takes input or binary information from multiple inputs and direct them towards a single output. So it multiplexes information from multiple sources into one output channel or line. So this is just a simple example. The number of inputs can be larger or can be reduced, and can be one of these input lines are actually connected to this single output line, and this is the job of combination circuits, and which are called multiplexers. Okay, so multiplexers are very useful combination circuits. They are used in different places, in communication channels and in computers and telephone and different other places. So we will see some examples of multiplexers in coming slides. So this is a very simple multiplexer, uh, which is a 2 x 1 2 into 1 line multiplexer, and for multiplexer MUX is used for short. So this is 2 x 1 multiplexer, and how to create one 2 x 1 multiplexer. So for 2 x 1 multiplexer we actually need two AND gates, and an input line is connected to each AND gate. So I0 is connected to this first AND gate, I1 is connected to this second AND gate. These are the two inputs, I0 and I1, and we should have a single output, and we should control how can we connect either of these inputs to that single output. So let me show you the output. This is the output. So the output of these AND gates is connected are connected to the OR gate, and a single output is taken from this OR gate. So either of these inputs can be connected to the output Y, and this can be controlled with select lines, and in this example there is only one select line. So this select line S, which is a single bit, can control which input of these two, I0 and I1 can be directed to output Y, or which of these inputs are selected to be connected to the output Y. And the logic is very simple. Here S is a single bit line, and this single bit can have two values. It can be 0 or it can be 1. So whenever this is 0, this inverter would convert it to 1. So a 1 is given to the first AND gate, and this 0 is connected to the second AND gate. So obviously the output would be 0 here, and this AND gate would function. So whatever the output is, the input is given at I0, that input would be achieved at output Y, and regardless of the value of I1. Similarly, so in other words, I0 is connected to Y. Whatever you give at I0, we get that input at Y output. Similarly, if S is 1, then the lower AND gate gets 1 from the select line, and 0 is given as an input to the first or upper AND gate. So it disables, this 0 disables the upper gate, and regardless of the input at I0, only whatever we give at I1, that is achieved at the output Y. So in other words, I1 is connected to the output Y. So this is a 2x1 multiplexer. This is the block diagram of this multiplexer. These are the two inputs of the multiplexer. This is the output of the multiplexer, and this is the select line. This select line, in this case a single bit, selects any one of these two inputs to be connected to the output Y. Okay, so this is a 2x4, sorry, it's a 4x1 multiplexer, but let me tell you how can we create this multiplexer from the scratch. So let me take a 2x4 lines decoder, and I will show you the procedure how can we make a multiplexer from this decoder, and also we can then relate to the size of the decoder, how large or how which organization or the what size of multiplexer can be built from a decoder. So we can establish a relation between the two. Okay, so this is a 2x4 lines decoder. So these are the two inputs represented with S0 and S1, and these two inputs are connected to the four AND gates, and these are the outputs. So this is a 2 to 4 line decoder. 2 are the inputs and 4 are the outputs of this decoder. So this is exactly a decoder. We have already studied decoders. So how can we make a multiplexer out of this 2x4 line decoder? Okay, so the simple procedure is to first connect uh, input lines to each of these AND gates of the decoder. So there are four AND gates. So four input lines are connected to these AND gates. One input is connected to the first, second to the second, third to the third, and four input line is connected to the fourth AND gate. Next, we just mark them with input variables I0, I1, I2, and I3. So we have now four inputs to this decoder. Now combine these outputs of the decoder through an OR gate and call them the output Y. So this becomes a multiplexer. How? These input lines of the decoder now are the select lines of this multiplexer, because these two lines, the value of these two lines selects any of these inputs to be connected to the Y output. So this actually was initially 2x4 lines decoder, but now this has become 4x1 multiplexer, because 4 are the inputs and 1 is the output. So it has become a 4x1 multiplexer, and these two are the select lines of this multiplexer, because these two lines can select one of these inputs to be connected to Y. So how it works? You can provide inputs to all or any of these input lines, but these two select lines will decide which input would be shown on the output Y, and this relation can be shown in the truth table as well. So S1 and S0 are the two select lines. So depending on the value of the select lines, we can get output at Y. If the select lines value is 0, 0, then only I0 is connected with Y. So whatever the value of I0 is, we get that at Y output. So whatever the value of I0 is, we get that at Y. So Y is equal to I0. So that means Y is logically connected with I0. Okay, so when the select line value is 0, 1, we get I1. When it is 1, 0, we get I2. When it is 1, 1, we get I3 at the output. So these two select lines can control which input can be connected to the output line. Okay, so this is a 4 to 1 line multiplexer, and we can create this from 2 to 4 lines decoder, as we just saw. Okay, this is the block diagram of this multiplexer. So it's a 4x1 mux. 4 are the inputs, and 1 is the output, and 2 are the select lines. Okay, similarly, we can connect an enable line with the multiplexer, just like we have seen an enable line with the decoders. So similarly, we can connect an enable line with multiplexer. So in this example, we have a multiplexer where we have a pair or group of 4 AND gates in the upper part and a group of 4 AND gates in the lower part, and we have a group of OR gates, and with each OR gate an output is taken from the upper group, and the second output is the second input to this OR gate is taken from the lower group of AND gates, and similarly for other OR gates. And the first group is connected to the A input variable A0 to A3, and the second group is connected to or identified with B Boolean variables B0 to B3, and we have select line which is connected after the select line with the upper group of AND gates, and after the second inverter with the lower group of AND gates. So it's a kind of S is connected after the when 0 is provided, 1 is given to the upper part, and when 0 is provided, 0 is provided to the lower. So when a 0 is given, 1 is provided to the upper group, 1 is provided to the lower group. When 1 is provided, 0 is given to the upper, 1 is given to the lower. So this select line can disable or enable either of these two groups, the upper group or the lower group. So it actually selects either of these two groups. If it is 0, the lower group is selected. Sorry, the upper group is selected. When it is 1, the lower group is selected. And apart from selecting any of these groups of inputs to be connected to the 4 outputs, either this group can be selected to be connected to the output lines, or the lower group of inputs can be connected to the output lines. This is the job of select line. But here there is an additional input which is called enable, and that is connected through an inverter with all these gates. So whenever we provide a 0, it becomes 1 after the inverter, and 1 is connected to all the AND gates. So when an input is 1 to an AND gate, the output depends on the other inputs. So when it is 1, it becomes 0, and 0 is connected to all the AND gates, and all the AND gates are disabled. So that means whenever an input, at least one input is 0 to the AND gate, the output is 0. So this enable, whenever this enable is 1, it becomes 0, and 0 is connected to all the AND gates, and the outputs are disabled. So regardless of the values of the inputs and the select line, when E is 1, it disables all the whole multiplexer, and it doesn't work. But when it is 0, the AND gates get 1 from this enable line, and they are enabled, and the output totally depends on the select line and the inputs. Okay, so here the function table or the truth table is given of the multiplexer. So E enable is 1. Whenever E is 1, it becomes 0, and the multiplexer is disabled. So regardless of the value of the select line, whatever the value of S is, output is always all zeros, because all these AND gates get at least 1 0 input. So the output is always 0, and when they are given as an input to the OR gate, they become 0. Okay, so all zeros at the output Y, we get all zeros. Whenever the enable is 1, regardless of the input X, the select line, regardless of the value of the select line, at the output we get all zeros. Whenever the enable is 0, from this enable 1 is given to all the AND gates. When the S value is 0, the select line is 0, it becomes 1 here. So the upper part is selected, the upper group of AND gates is selected, and the upper group of inputs, which is A, is connected to the output Y. Select A at the output Y. So when E is 0 and the select line is changed to 1, S is 1, we get 0 here, the upper part is disabled, and the lower part is enabled. So we get B at Y. So select B at Y. So that is the function table of this multiplexer, and this multiplexer is called quadruple 2x1 multiplexer. Okay, so Boolean function implementation. Multiplexers are useful circuit, and they can be used in addition to other function implementation. They can be used to implement Boolean functions. We have seen how to implement Boolean function with logic gates using classical map method, and now we can see how multiplexer are useful to implement Boolean function. So in general, any n variable function can be implemented with a multiplexer of 2 cross n to 1 size or organization. So for example, if we have 3 variable Boolean function, then that 3 variable Boolean function can be implemented with 2 raised to power 3 to 1. That means 8 cross 1 mux. But this is general principle, but we can do better. I'm not going into the upper detail to implement an n variable with 2 raised to power n cross 1 mux, but I'm going to explain the efficient solution to implement a Boolean function with multiplexer. We can do better. An n plus 1 variable function can be implemented with a 2 raised to power n to 1 mux. So for example, in the previous scenario, if we have 3 variable function, then it can be implemented with 8 cross 1 mux. But in the later scenario, when we have an n plus 1 variable, so 3 variable becomes, in the 3 variable case, n becomes 2. So then we need 4 cross 1 mux. So instead of having 8 cross 1 mux to implement 3 variable function, we can implement the same sized function with a 4 cross 1 mux.